Hey guys, so I just type up something on the chat. If you see them, can you echo back? All right, good morning. Yeah, so I'm not playing any more background music anymore because I did copyright claim on the video. Yeah, YouTube is very good. There must be some sort of AI running there. They can automatically detect all these copyright content. All right, so let's go ahead and start. So first thing is to go through the announcements. Yeah, as usual, you see the live video is here, Google Meet is here, and the assignment's due here. Now, I'm having a boldface around quiz 5 to 7 because it really depends on how we go today. We might end up doing just quiz 5 and 6 today. With that said, let's go to topic 1, which is what? Quiz number 5. Yeah, so we had too much fun yesterday playing with Google Meet. Oh, yeah, sure, of course. Yeah, they are very effective. It protects copyright from us as well. In a way, Poly will be protected if anyone copy Poly's video, right? And use that for teaching. Huh? So let's go ahead and enter quiz 5. Hi. Okay. Morning, Yuxiang. So quiz 5 is about delay, isn't it? Yeah, so we were talking about the performance metrics. Delay is nowadays the most important, most critical. People feel delayed, people hate delayed. So this is the output from a trace route from UMass to Oracom. So this is something very similar to what we show in the video. So for each hub, there are 3 measurements coming back from the hub, from the routers. So Q1 here in quiz 5 is asking, how come the 3 measurements are not identical, right? Every time the delay being the calculation of the delay results are different. Q2 asks, how come the delay measurements to hub 10 can sometimes be longer than 11? Hey, this is weird, right? Because hub 11 is certainly far away. In order for the packet to reach hub 11, they must have arrived in hub 10 right before that. So how come can the delays be sometimes longer to reach hub 10 than reaching hub 11? And could you come up with a method estimating the delay between hub 3 and 4? Because if you come here, okay, wait, give me a second. Because I want to be able to explain. So let's go to this bigger. Ooh. Wait. Yeah, bigger display of the quiz. You see here? Delay to hub 3, 655. Delay to hub 4, 16, 11, 13. Right? There's a link between hub 3 and hub 4, router 3 and router 4. You can essentially estimate the delay on the link by subtracting the 2 values. This pair of values, another pair of values, right? That's one way. But there could be other way. For example, you take an average of 3 measurements, subtracting the average of 3 measurements. Okay, so calculating delay between link, hub 3, hub 4, there's probably an easy way, isn't it? But can you use such a straightforward method to calculate the delay between hub 8 and 9? So hub 8 is here, hub 9 is here. 104, 109, 106. 109, 104, 102, and 104. And you go, whoops, right? If you do average, delay to hub A versus delay to hub 10. This is actually longer, and this is shorter. Yeah, and because we kind of reveal quiz 5 a little bit earlier. So I guess many of you guys have started working on it. So why don't we go ahead and just look at what you guys have on Slack. All right. Okay, so this is from Team 5. Let me go all the way to the top. How about that? Okay, so this is Team 1. Team 1 say, one possible reason that the delays are not all equal is because the queuing time, for the 3 different trial could be different. Yes. Oh, there's another reason here. Yeah, they might be traversing different paths, as you see in pollys demonstration. It's nowadays quite common to see packets, although going to the same destination, but in the middle of the internet somewhere, they actually go through different paths. And I think there was a question raised yesterday on Ask Us Anything. So I tried to explain. A lot of times, some of the big routers in the middle of the internet try to do load balancing. Yeah, so there are multiple links going out, and they can both go to the destination. So they do load balancing like this. Some packets go this way, some packets go that way. Q2, router 10 may be busier. Yeah, at the time of the 3 trial to router 10, isn't it? By the time the 3 trial to router 11, router 10 might be no longer busy. Very good. Yeah, the loading can be different from time to time. And the difference, you will be surprised, can sometimes be very large. So let's see what Team 1 say to calculate the link delay between router 3.4 between 8 and 9. So, okay. So Team 1 suggests this. Yeah, take the average of the differences, isn't it? Oh, and Team 1 divided the average of the round trip delay differences by 2, because round trip is what? Going and back. So the delay over a link is just one way. So divide it further by 2, then that's one-way delay. Very good. But for the delay between router 8 and 9, they only take one value. I guess this is the difference between the pair of delay that they see that router 9 shows a longer delay than router 8. Because the other way around is just not reasonable, isn't it? Yeah, so you remove some outliers. Okay, that's one way. Team 13, let's see. Yeah, similarly. Okay, Team 13 here takes a similar approach, right? Removing the outliers and take only the measurement that's a little bit more reasonable. Let's see, right, how other teams propose different solutions. Use the same method above on 8 and 9. If the number is negative, is higher, we should try more times. Okay. So Team 7 here, the approach is a little bit different. They still take the average of the 3 diffs, okay, or the average of the 3 samples and take the diff of the average. But in case the result is negative, they would fall back to something else, saying that maybe we take more measurements until the diff is no longer negative. Okay, so this is nice. Did I say good? I think I clicked monkey. Yes, I did. Okay. You Quan is taking a very common approach, like the first team, and I think Team 13. Okay, nice. Yeah, so Team 2 here. Okay, Yunqi, representing Team 2, says calculate the average of the diffs or the averages of the delays and calculating the differences. All right. Okay, so it's pairwise diff, an average of the diff. And then only take the pair that's making sense. All right, so as I went through many of you guys' solution, I see very common, right? Remove outliers, one major approach, or taking more measurements, okay, and then take average of that. Okay, either way would work. Okay, and I think that's probably enough discussion. Let's come back to the lecture. Yeah, I still don't know if the time is for round trip or one way. Yanjun. Yeah, so that delay we see from trace route, that's round trip. Okay, and the delay I was asking for, generally when people ask delay, it's just one way. If we ask for round trip delay, usually we say round trip delay. All right, so let me know, Yanjun, if that addressed the question. Yeah, I know sometimes when we say things verbally, it's a little bit fuzzy. Okay, let's go ahead and talk about the two other metrics. They are fairly easy, and let's start from the packet losses. Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case a packet arrives when the queue there in the router is already full. So you see this blue packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we will not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission. Throughput is the third metric. And it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end, and the speed of data is going through the entire channel, entire pipeline. Now, there are two ways of quantifying throughput. One is called the instantaneous throughput, the other average throughput. Now, the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discussed throughout the rest of the sites will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of F bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network. And the link capacity for the link directly adjacent to the server is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider, okay, such a data pipeline as a fluid pipeline, water pipeline. Then you see, I'm drawing, okay, the pipeline's width, the diameter, based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? Okay, a water tank, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS? Well, it's probably not that hard, isn't it? Because the intuition tells you that, hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Okay, even though RC is bigger, yeah, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, yeah, there could be a lot more water coming in, okay, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, okay, RC is going to be the throughput. And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. Okay, so throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, okay? Deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, okay? Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end-to-end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. Okay, RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming the 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this, minimum of RCRS and R over 10. In practice, however, okay, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an end system, this is an end system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays, there are a lot more connections sharing the big R. Okay, most of the time, RC, RS are the bottlenecks. But occasionally, you might also see when network is really congested, R is not quite enough to allow all the connections demanding services. There, loss and throughput. We now switch gear a little bit, but before that, let's go over the questions that was popping up earlier. Okay, so yeah, there was a little bit of confusion between when we say delay, is it round-trip delay or one-way delay? Normally when we say delay, it's one-way. Okay, if I want to ask about round-trip delay, I ask round-trip delay. Tony here asks, can the go and back during the round trip be different? So even if they are on the same route, okay, going and back, the delay can be different, right? Because the timing are different. Even the same path going can also be different. Actually, Tony extended, can the route be different, right? The route going versus the route returning from one of the hubs, can they be different? Yes, they can be different, and probably more often different than you think. Jiayo was asking, RS and RC, the client-side bandwidth, RS and RC, the server-side bandwidth versus the client-side bandwidth, which one bigger? Typically, the server-side bigger. Okay, so people who provide service oftentimes subscribe to higher bandwidth to make sure that the services are smooth. So I think Chen Tao here asked the same question. And I ask, now with also these middle pipes, okay, these are usually the global ISP pipes. Those are typically the biggest. But you want to think again where the bottleneck is really at any given point in time on the internet. It can be anywhere. When there are too much traffic crossing the global ISP, bottleneck is there. When there are too much service demand for the server, RS might still be the bottleneck. Okay, and RC can sometimes be the bottleneck in case the streams you're downloading is too much. For example, every one of the members at the household are watching something, 4K, for example. And if you are using LTE 4G to watch a video stream, definitely I think the bottleneck is more on your LTE link. That will be RC. I think Liang Yu was asking, RC will not be influenced by the timing of the day. Liang Yu, you are perfectly right. So the last part that I was trying to explain is exactly this. At a particular time, the bottleneck can be RC, can be RS. Yeah. Because when there are more traffic on the pipe out of the server, the RS will get smaller. Because RS and RC, if you think about it, it's a little bit more dynamic. What kind of things could determine the number of... Yeah, so your subscription to the service, as well as the cross traffic. All right, I hope those address the question. How can we increase our RC? Oh, you pay more money, then you get more RC. Or you force your other family members to not watch video and only you can watch. Then you see the stream rate is higher. Yeah, so that's pretty much it. Okay, so let's switch to topic 3, Internet Service Model. 1.5, Protocol Layers and Service Models. Well, this is a very special section. There's not much really technical here, and the purpose is essentially to explain more. You'll see later in chapter 2, 3, 4, 5. The chapter's title is called Something Layer, Something Layer, Something Layer. Okay. We kind of talk about all these internet protocols or internet mechanisms by grouping them into layers. So chapter 2, we talk about protocols running in a particular layer. Chapter 3, another set of protocols running in yet another layer, and so on and so forth. So 1.5 here is to give you an idea why we kind of classify protocols into layers and what does each layer do in terms of functionality, making sure that the internet operates seamlessly. Okay, so we call that the service model, the internet's service model, or the architecture of how we organize softwares running on the internet. And to explain, let me use an example. Traveling by air. Let me try to use an analogy, air travel here, to show you that it's kind of important to have some sort of organization, some sort of architecture, okay, to make sure a complex system will work seamlessly. And you will see also air travel and internet. Okay. Air travel to communicate people, internet to communicate data. They are somewhat similar, and therefore the architecture used by air travel is similar to the architecture used by the internet. Yeah, by architecture here I meant the service model, the way the service operates. Good. Now, recall your experience traveling through air. First thing you do, purchase the ticket that guarantees you a seat. At the day of travel, you walk up to the counter, you present your passport and the ticket number. They will allow you to check in your bag and give you the boarding pass. With that, you go to the gate and they let you into the plane. And then the pilot will be negotiating with the traffic control of the departure airport and decide which runway and at what time the plane can take off. And then for a long time, you're just sitting in the cabin and try to get some sleep. But the pilot is busy doing this. Okay, routing the airplane. Okay, so as the plane crossing border of some air control, communications will go on again and making sure that the planes traveling the air, the space, will not collide to each other. And hopefully everything is fine at the arriving airport. Again, pilot talks to the traffic control and find out the runway and the time to land. When the gate is connected and open, we may now leave the plane. Most of us go to the baggage claim to pick up our bag and exit the airport. So it looks like it's a series of steps. Very simple. But if you think about it a little bit more, right? Purchasing the ticket is important so that it guarantees you a ticket. So that when you go to the counter, when you're trying to check in your bag, they recognize you, right? And the base of the recognition is on the ticket number, okay? Acquired here and checked here. And in return, you get a bag number, which is used again here. You get also a C number, which is used again here. So there are still some communication that needs to be done, for example, between the steps, in between these two steps. Okay? So this component here, more closely related to this component. This component here is also more closely related to this component. And this component also connected and related to this component, even though this is at the departure airport and this is at the arrival airport. Okay. So you see that there are components that are related and there are some base in order to communicate between the staff members here and the staff members here. Okay, the mechanism here and the mechanism here. But you see also, for example, baggage check here. Well, it has less to do with the pilot communicating with the central control. Okay, you see also a little bit, right? This is a little bit more like the internet core. The functionality is quite different. But these are a little bit more like the edge of the internet, where you're trying to track data. Here we're trying to track passengers and the belonging of the passengers. Okay. And so that it's probably not that hard to see. There's a architecture there, okay, and it's kind of laid out in layers like this, right? This is communication to traffic control, but at the end, communication to air travel on the other end. Communication of air travel, but from region to region to region to another region's traffic control office. Okay. So to regional office, it's just to make sure that the height and the orientation of the travel is correct. Now these involves also runway. So you see there's slight differences between these two layers. Now these three, okay, are more handling the passengers and baggages, not handling the plane per se. Okay, so which gate we get in and which gate we're coming out. So your families and members will know where to go to pick you up, for example, to welcome you back, for example. And baggage here, the number is important. At the destination, you also want to know which station is for the baggage claim. There are usually multiple of them, right? So it's also based on the plane number, the flight number. Similarly, ticketing. Sometimes you need to delay travel, right? So you need to call the ticket office again to try to change the day or change the class, okay? And the reference is always, for example, the ticket number, okay? So for communication, you need certain important IDs, important information there, okay? To communicate within a layer, okay? The claim ticket there for the bag is so that you can pick things up on the other end. But there are also certain numbers. For example, ticket number connects to a bag number. Ticket number also connect to a C number here. Okay, so certain pieces of information might be added there, either to allow communication within the same layer from local side to remote side, or information to allow components across layers on one side to try to relate to each other. Okay. So you see, air travel, okay, is a complex system. If any step goes wrong, it could end up being a disaster. Okay, needs to be well structured to make sure also that it's efficient. So there are layers. Each layer implements a particular function, okay, a particular subservice, okay? And so there'll be some internal actions, but they will also depend on services or functions provided by the neighboring layers, okay, from the layers below, okay, or they might also need to provide supports to layers above. So that was the air travel example. So internet actually borrow a similar approach and layer the various components. So next, let's talk about the benefits of doing layering. Hopefully with the air travel example, you see in a large complex systems where we have lots of these pieces, it's really good to have some explicit structure so that it's a little bit easier to identify in case there's a bug, which piece the bug is, and to find out what are the related pieces might be partly to blame as well. So having explicit structure, really good. And you see in the air travel example, we have this layered architecture, layered service model. That's exactly what we're using, okay, to manage, to organize internet's operation. And we call that layered service model also the reference model, because we are referring to these pieces on the internet in layers as well. Okay, so it's our reference model for discussion among the network engineers, okay, which you are becoming one as well. All right. So this way of trying to break a large complex systems into pieces, okay, and to define, okay, the functionality of each piece is also called the modularization. All right. So after defining the functionality of each pieces, after finding out the relationship between the pieces, okay, we implement the individual modules functionality. We also implement the interfaces to communicate from module to module. Okay, so that is called modularization. Okay, this is really common. We see in large software systems, okay, because it's a lot easier to maintain. It's a lot easier to debug problems, and it's also a lot easier to improve the system, to move a complex system forward. Okay, because you see, the important functionalities are well modularized. So if we need to change the way we implement the functionality, we can just change it. Okay, and that change does not need to propagate through the entire system across the different modules. Okay, so a change, okay, in a layers service, a change within a piece, a change within a module, okay, can be transparent to the other modules, okay, because the APIs are already well defined. There's minimum communications required. All right, so it's just like this. Here's an example. If we change the gating procedure and we decided that we let the first class passengers to go last, hey, it's not going to change how the pilots communicate with the traffic control, right, in order to find out which runway to take off. So each module more or less independent, and the communication across modules, across layers are minimal. Modularization or layered reference model, layered service model. Sounds nice. Can you think of anything that suggests such a layering is not exactly good? All right. Yeah, and finally we talk about how internet are layered. Internet protocols are layered. Okay, so here it is. Here's the internet protocol stack, and you see here what I'm illustrating. It's in the layered architecture. The layer at the top is the application layer. So these protocols at the application layers are, okay, literally to support the applications. For example, HTTP is supporting the web application. So you do have application processes sitting on the web browser side and another application layer process at the web server side. Okay, and there's a protocol there. For example, a message go out is necessary from the client to request for a web page, right? And that web page will be another message coming back the other way. Well, that's pretty much what HTTP defines, right? So these messages to control when to start sending and which web pages to send. Transport layer, that's one layer down. Okay, the functionality is essentially to allow these application layer protocols to specify, okay, whether these data that I'll be sending through, these data packets I'll be sending through the internet is gonna be reliably transferred or best effort transferred. Okay, so this is to administer data transfer from client to server process or vice versa. Network layer protocols, on the other hand, very special. Yeah, all these packets, oh, by the way, packets, when it arrive at the network layer, it's called another name, datagram. So these packets coming from the source, right, needs to find a way to the destination. You see, at the core of the internet, we do have a mesh of interconnected routers, don't we? A router could have multiple connections to other routers. So each router will need to know, okay, which is the right router to forward next so that the packet will arrive at the destination with the shortest distance possible, right? Because you do want the packets to arrive at the destination as soon as possible. So a good routing protocol is to ensure something like this. So network layer, the protocols there are essentially to handle packets being forwarded and the directions of how these packets being forwarded in the core. Link layer protocol. Okay, so these are very special. They work a little bit like, honestly speaking, the transport layer protocols. Okay, transport layer is to handle data transfer from one process to another. Link layer protocol here also handle data transfer. but it's between one network element to another one network element. One network hardware to another network hardware, or a network entity to another. For example, between two routers directly adjacent to each other, there's just one link. Okay, so this might across several hops at the transport layer, but link layer protocol only handles data transfer in one hop. Okay, so it deals with the data transfer very locally within a link. For example, Ethernet is a link layer technology, a link layer protocol. Yeah, so that was Internet protocol layers. Now the next video is to try to combine everything. So in 1.1 to 1.4, you hear 1.1 to 1.3, you hear more about the nuts and bolts, the physical infrastructure. But then starting from 1.4, you heard about protocols and then how you evaluate protocols using different performance metrics. Just now you heard about that we actually classify the protocols into layers. Okay? So there are software side protocols structured in a layer way. Physical side, hardware side, where you have cores, edges. But how do the software and hardware integrate? So we'll see how a packet, how data travel the software stacks, and then through the physical infrastructure and up and down some additional software stacks, okay? And finally to the destination and again up the software stack. So this is to provide you a more integrated view of how data travel the physical internet and the software stack. With the layered architecture explained, what I'm showing here is the software side of the internet side by side with the hardware of the internet. So where are the hardware in this example? Look, here, and here, and here. So these are end systems, okay? This one is the source, and this one is the destination. You see that at the end systems, the entire internet protocol stack is implemented and running. Similarly for the other end system. But in the core of the internet, you see the router over here, and this is a very special entity, hardware entity. It's called switch. But to be precise, this is the link layer switch. Its functionality is limited. Okay? Unlike router, this is a network layer device that implements the protocol stack from the lowest up to the network layer. The link layer switch is a more limited device. It implements only from the physical to the link layer. Well, then you see how it gets the name. It's a link layer switch. And if you want to be precise, you can also call these routers the network layer routers. Or sometimes we actually call these routers network layer switches. Okay, so both of these entities are doing switching, but doing the switching at a slightly different level. All right, now walk with me and let's see how the data gets passed down the protocol stack, out of a physical entity, and through the network, reaching the destination. The first step is this. Yeah, one particular user typing things up. So at the application layer, this component generates a message. Yeah, a packet at the application layer is referred to as a message. The application layer component will pass the message down. As the message arrives at the transport layer, a header is being appended in front of the message. Okay, because it's appending, therefore these additional pieces of information is referred to as the header. H stands for header. And this is a header appended by the transport layer, therefore HT. The whole thing together, this packet, is referred to as the segment. So a packet at the transport layer is called a segment. And you see that this header here is very important. This is to allow the transport layer component at the source side to communicate with the transport layer component at the destination side. Okay, so this is a little bit like at the airport when we're checking our bag. The counter is going to give us back what? The passport, the e-ticket, and what? The baggage claim ticket. Okay, so that baggage claim ticket, that additional information, okay, in order for you to find your bag, is a little bit like the headers. Okay. And now the segment is going to be passed further down to the network layer. And guess what? The network layer component is going to append some more information to it. And that is in the header as well. But this is the header for the network layer, HN. And the whole thing now, the packet here at the network layer is called a datagram. And the whole datagram is going to be passed down further to the link layer. And guess what? The link layer header is going to be appended, and we call a packet at the link layer a frame. So this frame here, now arriving at the physical layer, what physical layer is doing is simply modulating the 0 and 1 bits, okay, onto the physical media. So it's going to go out shortly through the network interface and arriving at the router here. Now I'm skipping the switch here because it's a link layer device. We'll not be able to cover the link layer chapter. So this message is going to arrive here at the router, receive at this physical layer, and the signals gets converted to the digital form. So we restore the original frame back, and that's passed up into the link layer. The link layer at the router is going to examine this header and see if there's any additional function that it needs to perform. When everything is done, guess what? Okay, this header is going to be removed. So only the message with the transport layer header and the network layer header will be passed up to the network layer. You see here, the message is being passed upwards, okay? Because the network layer component of the router still needs to check this, okay, and see if there's something that the network component needs to do at the router. So this is going to be examined, okay, and functionalities performed. Now this part, hey, as this is a router, there's no other layers above. So this is going to be copied over, okay, and stand by there at the outgoing interface. Now before that message go down to the lower layer, the new network layer header is appended. And this one is a datagram. It gets passed down to the link layer header appended. And this is a frame. It goes to the physical layer. Bits modulated, traveling the link and reaching the destination. Similarly, the physical layer is going to recover the 0 and bits and give this up to the link layer. This checked by the link layer, and the remaining gets passed up to the network layer. And you see this removed, this part gets passed up to the transport layer. This removed, and this part here gets passed up to the application layer. And here, the destinations processed there at the application layer, finally you see the message coming from the source originally. So this is how a message travels through the protocol stack and the physical infrastructure and more protocol stack up and down until all the way up to the application layer and the destination. All right, so that was, in fact, chapter 1. We'll skip the security subsection The videos are all there from the course page. We just don't do it live because those are very, very high level description of the common security threats. Let's take a break and we'll open chapter 2 next hour. So it's 11:09. That's return at 11:19. So maybe I can go over a little bit of the questions that are being raised in between. But let's take the break first, and we'll go through the questions. If you have follow-up questions, feel free to type things up. I'm feeling that you guys probably prefer asking question over chat, right? Because you can probably elaborate. If it's real time, it might not be that easy. So break, feel free. And let me go get water, and then I'll come back to address the other questions. I think there's one more from Bing Ray and one from Boris. Interesting. Okay, I really hate typing Chinese. Yeah, so that's my major deficiency. Okay, it's 11:19. That's resume, and that's first go through the questions asked. So, by the way, I'm really happy to see that you guys don't mind asking questions, and as soon as you come up with something, you type it up. That's great. That's the way, the right way to learn, by the way. And so, first is Liang Yu asking. Okay, so I'm not quite sure why Ethernet is link layer, because video was, when I was doing that part, it goes really fast. Yeah, so think about how you use Ethernet, right? You use it to connect your computer to a router. Well, you don't see the router, but you plug the other end of the Ethernet cable on the wall. And there are wires embedded behind wall and connect to the router somewhere within an EE building. Okay, so if you think that way, Ethernet is a cable, a link connecting the router to your computer. Okay, Wi-Fi does the same thing, essentially. So there are other kinds of cables you could use. Access network is also link layer. LTE, therefore, 4G link layer. Okay. And Bo-Zhi here asks, so he's not quite sure what I meant, right, in the video. Handling communication process to process. Okay. So what I meant by a process is if you start a web browser, right, it's a process running on your computer. And it's actually interacting with the web server of the page you are clicking. So that web server is a process running on the big server machine. So there's communication between web browser and the server process. Okay, so that's what I meant by process communication. And application layer protocol as well as transport layer protocols handle process communication. Okay, network layer, I said computer or end-to-end communication, because network layer is there to find a path from a source to destination. So one computer to another computer, not particularly the processes running on the computer. In a way, if you have multiple web requests, okay, to the server running on the big server machine there, then you have two process communications. But you see, from your PC to the big server machine, it's just one path. Okay, so network layer is to try to find that path, and therefore it handles the stack from machine to machine, end to end. Bing Rui is asking a very interesting question. Some of you probably had these experience playing with the microcontroller systems. We use I2C or Uart to connect sensors to these microcontroller systems. We sometimes use Uart as well to connect an additional gadget to our PC. Okay, it's just that nowadays we use USB more than Uart or I2C. So Uart and I2C are more used by the microcontroller systems to connect to the even simpler sensors. Okay, so then the question was, is I2C Uart a link layer protocol, or is it a physical layer protocol? Okay, so it took me a while to think about it, but I find this a very interesting question. Okay, typically people don't use Uart or I2C to connect a device straight onto the internet. Okay, so we don't usually see I2C Uart as a link layer protocol, but it's very similar to a link layer technology, however, right? It's allowing one electronic device to connect to another electronic device. Okay, it's a link layer technology in a general sense, but probably internet people won't mention I2C Uart as link layer protocols. Chen Tao was asking, when data are passed down the vertical layers, we just put additional 0 and 1s in front of the data. Yes, okay, because yeah, so if the data is encrypted, yeah, of course, the other layers don't necessarily need to look into the data, but just add additional informations allowing this end of the protocol to communicate other parts that will be interacting with this end here. Okay. Hey guys, I'm so happy to see that you guys can't wait to learn, because many of these questions you ask, I will answer them, but in the videos in chapter 3 or chapter 4. And some of you ask questions in chapter 5. No problem, no problem. Just say it, then everything is clear, and then we move on. Okay. All right, so let's start chapter 2. How about that? Okay. One disclaimer that Polly needs to say is that Now, the set of videos you'll be seeing were the videos that Polly shoot at the very beginning that Polly needs to shoot videos. Okay, so you see that Polly is a bit rusty, and she was not acting exactly naturally and feeling awkward. So I thought that it doesn't hurt that you see that it's okay to embarrass yourself publicly. So now, okay. Section 1, yeah, a lot of basic terms, concepts, design elements, design considerations. We're going to spend quite a bit of time here, in fact. Okay? Just be prepared. And then we'll be spending also some time in chapter 2.2. This is one of the key applications supporting actually our everyday life. That is the World Wide Web. And the application layer protocol that's keeping the web running is this, HTTP. Now, I'm going to insert one more protocol which is not touched on in textbook called the FTP, as that some of us are still using it a lot. Okay? That is mainly a protocol to support file transfer, such as what's implemented in FileZilla. And the secure version of it is called the Secure FTP. 2.3, we'll be learning all these protocols to support email. So many of us write emails a lot. I guess some of the younger ones are no longer writing emails, but many of us, especially professional people, are still using a lot of emails. It's very good to know how email system operates. And then DNS, I try to explain extensively up there. It's a huge architecture behind DNS servers. You do want to know how the DNS servers are interconnected. That's going to help you design applications as well, even though it sounds like a sort of a core services to support internet operation. Not exactly an application. And then 2.5, you will see how P2P networks can be designed, how P2P services can be designed. We'll also see a couple examples. One of them is called the BitTorrent. So that is the major P2P services that's before Bitcoin. We're going to see what's behind BitTorrent's operation. We'll also describe a bit more of another P2P application called Skype. And then we'll also be spending quite a bit of time here in 2.6, as many of us are using streaming services over the internet extensively, such as YouTube, such as what you're doing now, watching the online lecture, right? So we'll be doing video streaming, and content distribution network is there to support video streaming. But let me just say that although we say that content distribution network is there to support video streaming, but most of these streaming services are operating based on the client server. Just to clarify, it's not like that the content distribution network is an architecture itself. And then briefly in 2.7, we're going to introduce the concept of socket programming. But much of this I'm going to just duplicate and repeat again and again in PA 3 and 4, where we'll begin to do socket programming as we go, right? But in chapter 2.7 and 2.8, you will see the goal of the textbook author is so that we take you through how one implements a web server using the network socket. So one could do this using other programming languages, not only the Golang, such as Python, such as Java. Okay, so Golang, I try to justify why we use this language at the beginning of the semester. Now, let's move on. Before we talk about the concepts, let's talk about these applications so that you get a better idea. I keep saying network applications. What are these network applications? Well, first of all, look at this, email. Some of you have emailed me before. So those email clients that you're using to type up your emails, yeah, that is part of the email services. part of the email application. And going to the course page, for example, then you'll be using the web service. Text messaging. Yeah, some of you guys might be now typing live on the live chat. That is a text messaging service. Now, some of you have already messaged me through the messenger, okay, the Facebook's messenger. That is also a text messaging services. For many of the domestic students, you guys are probably lining each other a lot. So Line is one of the most popular text messaging app in Taiwan. Remote logging. Yeah, let's see. Have you done this before? Oh, yes, you did. For PA1, PA2, I think you've tried it out already, right? Doing SSH. Yeah, SSH belongs to also this category called the remote logging. It's just that the SSH is more a secure remote logging. P2P file sharing, if you have experience using BitTorrent before, then you will see what I'm saying here. A peer-to-peer based file sharing system. Bitcoin is P2P, alright, but it's not exactly file sharing, but it's more directory sharing, content sharing. Okay, so yeah, you can think of P2P file sharing a bit more generally as P2P content sharing. So those are very common. The next few, it really depends on your habit. You might use some of these more than we do, but you might also use these less than we do. So first, I see that I think some of you uses these more, the games. The mobile games or the regular online games you play on the desktop. Those are multi-user network games. So some of the architecture of these multi-user games could be quite complicated, and transmission of the game data can also be a bit hard to do. Right. Next, YouTube, yeah, streaming stored video. So streaming services, there's a more official name, streaming stored video. And then over this side, right side of the slide, you see, these are for the teleconferencing. So voice over Skype is one of the teleconferencing means. In fact, in Skype, you can also do video conferencing. Nowadays, we have Zoom. That's another choice that's popular. Google Hangout, some of you might still be using it. I think there are more and more rising these days with the virus situation getting worse. So the university is advising us to use this system called the U system. Well, maybe eventually we'll give it a try, but for now, just so that you know, U is also one of these teleconferencing services. Now, well, there's video, there's audio, but they are not quite streaming stored video we were talking about here, because these audio video are actually very interactive live. Not quite like what we're doing here. We're actually doing it semi-live. Having 10 to 20 seconds delay, it's barely live. Sorry, it's barely real time. And then social network. For this course, sorry, you have to use Facebook a lot. Well, Facebook is quite reliable, although that it has less regard about our privacy. Hopefully you don't mind too much being on Facebook just for the semester, all right? So social networking, Facebook. I do know that many of you are on IG, right? So I've been asked a lot to, start my IG account, but I'm still resisting it, all right? Just to tell you, as a fact, Polly is not a very social person. From time to time, I really like to be alone. I don't know about you. Some of you might be as well. It's actually really nice if you think about it. Give it a try. And then searching. I don't have to say too much about this. Yeah, Google Baidu. Yeah, there are just so many of them. Okay, so searching engines. And last, cloud computing. Well, some people actually consider P2P as a cloud computing services. And some also consider streaming services over here, for example, Netflix, YouTube, also a cloud computing service. Because it's essentially a number of machines forming a cloud. So it's not quite entirely the internet, but it's a subset of the internet there supporting the operation of a service. And that is not quite like the client service model. Hey, there's one system being client and another system being server, and there seems to be only two entities involving the service. So cloud computing in a very general term, that means there's quite a bit of nodes involved, quite a bit of end systems involved, and they're forming this cloud. But these days, when people talk about cloud computing, they might mean more specifically Amazon's AWS service, okay, or Microsoft's Azure service. Yeah, so these are the cloud computing services. So these companies allow us to subscribe so that we get to operate multiple machines that are physically across the world. So you could kind of build your systems, build your content distribution network in a way. All right. So yeah, cloud computing, it's a term that's a bit fuzzy and sometimes general, sometimes more specific, pointing to these cloud computing services. Well, they don't charge people though. Okay. Right, so going through these examples, so just that you have a good context of what we're going to talk about. Okay. Now, implementing these applications. To create such a network application, you do need to write programs. All right. So these programs will all be running on the end systems. So let me bring up the animation. So end systems, here, here, and here. Okay. And they'll be communicating over the network like this. End to end. End system to end system. All right, so for example, this guy here could be the web server, and this guy here could be using Safari to look up the course page. And there's communication going through the internet such that the web request goes to the server and web server here replies with the course page. All right, so you do have the web server software here running on the physical machine over here. And then you do have Safari, the web browser software that's implemented and running here on the end system. Okay, so programs are distributed, in fact, in a network application. And there's not going to be need to write a software so that it runs in the internet core. So what are the internet cores? This is the internet core. And there's not going to be any part of the software that involves operation of an application layer protocol that's going to go in here. This is actually a very nice consideration when we're designing how to build network application, because then we involve very little entities that we need to change in case we want to evolve or we want to update our application. Okay, so the core devices do not run the user applications. Therefore, when we want to make rapid changes, we don't have to change all the codes that's running here. So that will require every router here to make changes. Okay, so if we want to make changes on the apps, designing it this way, having all the software running on the end systems, we just need to update the end systems. Nice and independent. And that takes us to the first quiz.
Well, actually, second quiz today. Oh boy, I really need to replace that video. Okay, but let's move on to quiz 6.
So this is an interesting quiz. Every year, Poly surveys the younger generations what kind of apps you guys are using so that I stay in sync. So a nice thing teaching in college is that I have access of you guys. So Q1 asks you list 2 apps that you use on PCs or laptops. Q2 asks the 2 apps you use on smartphones when you're more mobile. And Q3, 2 games that you play, okay, on any of the platforms. And we can move to Slack because I see this should be a relatively easy quiz to work on. You just need to speak what you do. So let's see. Team 13 here says Line and Facebook for PC or a laptop. IG and Facebook. Okay, I guess Team 3 is very social. So probably not. Game, okay. LOL, I know this game is so popular in Taiwan and maybe Korea. Okay, so every year I see interesting games. And as years go by, I see the popularity of the games gets more diverse. I often see games I've never heard of. It might be some new games, okay, that just appeared. So Fate and Grand Order, interesting. Okay, so it's probably one of the smartphone games. There's so many smartphone games these days. And Team 2, Facebook Line, IG and YouTube. Yeah, I do YouTube a lot as well. So social and audio video and texting as well, but social texting. Okay. Game. Okay, I don't know what's Overcooked. It's probably a web game. But Minecraft, this is another popular game, but this is popular worldwide though, Minecraft. Team 4 from Weiyo. Chrome and Facebook, yeah, of course, right? Web browser, very, very popular. Facebook, YouTube, and Instagram, video and social. And social in a multimedia way with lots of pictures and stuff like that. Clash Royale, yeah, this seems to be a popular smartphone game. I've seen it multiple times. I think it appeared last year as well. Brawl Stars. I don't know exactly what that is. Interesting, just to see. So Notion. Okay. So I think it's a productivity tool. Yeah, I've seen other students using them, and they like them, like Notion. But would Notion allow group productivity? Okay, let me know, Team 15. Chrome, yeah, of course. Facebook and Line. LOL again. And Maple Story. Hey, you know what? Holly plays Maple Story as well, but it was a long time ago. It was really fun when I'm in a team. And I often team up with like 5-year-old kids. It was super fun observing how they play. I couldn't get enough of playing with those kids. Team 7, YouTube. Oh, Netflix, right? A little bit like YouTube, but Netflix provides really nice content. Okay, interesting and new. Squid Game. Is anyone following it? IG and Facebook. LOL, the mobile version. Okay, good. Nice to know. Thank you, team. Harry Potter Magic Awakened. Oh, okay. Is this a mobile game? Sounded like a mobile game. Team 7, FIFA 20. Yeah, all right. Yeah, sports game, right? Shooting hoops, soccering. Yeah. I love Maple Story. We might have played before. 'Cause when I was playing it, I was close to 40. Yeah, you were probably 5. Shanting. Yeah, it was really fun. The kids are really cute. They say the most interesting things. Okay. And they never fear asking questions. They probably feel that I'm adult, and they ask all sorts of questions. Team 1, Yuxiang. Safari, a different kind of browser. Facebook, Netflix, YouTube. Oh, okay. So this is the game, Magic Awakened. I guess it looks a little bit more like a role-playing game. Oh, I love role-playing games. I used to be a hardcore player when I was in the 20s. So I needed some games to take me through the PhD. I need to let the certain part of the brain rest, and the way I forget about those things is to play game, right? So you get diverted to something else, and when you're done, you get refreshed. You might be, Shanti. So if they do well, I actually distribute the loots I have collected previously. They all like that. I'll just, throw stuff away outside, and they will all go pick things up. Oh, maybe. Hey, Chen Tao, you might have played with me before. Okay. All right. Safari, YouTube. I think I went through you. Oh, did I? Okay. So I jumped a little bit too fast. So Team 10, Youting, Chrome, and Netflix. Yeah, I think I do Netflix, YouTube on laptop at least, or desktop, because smartphone screen is just too small. Even the largest is still too small for me. Mobile, yes, I do Line also. I hated it, but I have to. IG, no, not for me. Brawl Stars, this is the second time, right? NBA 2K, nice. Yeah, I like sports games too. Safari and YouTube, IG and PTT. Wow, okay. I guess there's now there's an app for PTT access. That's cool. Gardenscapes, 20. Okay, so Jiawen, you play all the interesting games I've never heard before. Mingxian. My brother all agree that game is that's a shitty company. We can say that. So I watched Dinter's video about the probability of opening boxes to get some rare treasure. Yeah, it's not very honest of them, right? Oh, go look it up. Dinter's YouTube channel. So he's really interesting. He's a very interesting guy. He actually experimented, spending lots of money. A very good experimentist. Okay. Mingxian, Chrome and YouTube, Line, IG, LOL, Apex, best game ever. Okay, so that that raised my interest here. Apex. Okay, I need to look it up. Apex. Oh, interesting. 小对峙大逃杀. Oh, interesting. It's a little bit like PUBG, I guess. 大逃杀 games. Yeah, I love those games. It was a lot of fun. Okay. Using the pen, right, to attack each other. YouTube, Twitch. Oh, okay, Twitch. Nice. Reddit and Instagram. Yeah, I didn't know that some of you follow Reddit. It's a place that I go very often as well. It's a little bit more like the techie people's PTT. Pokemon Unite and Valorant. Okay, so I know there's many variations of Pokemon copyrighted games. Okay, so this sounds nice and, violent, but I don't know exactly what that game is. Line, Facebook, Line, Instagram. Mingho, you do too much Line. Identity 5 and Minecraft. YouTube. NTNTU, what is this? I didn't know of this. Li Jun. And you put a crying face there. It doesn't look like you like it, but you have to somehow. Okay, let's look it up. Maybe I'm the only one not knowing what it is. Is it my NTU or MTNTU? Probably typo. Yeah, okay. Discord, okay, yeah, there's an increasing use of Discord from Taiwan. It used to be just gamers, but people are now using Discord also for productivity and team purpose, because the voice communication there is really smooth and nice. Google Map, oh yeah, I do that a lot. Clash Royale again, Apex, yeah, that was the popular game, the best game ever that the other game mentioned, right? Mingxian also mentioned that. Very good to know, and this is a very important quiz that worthwhile spending time on. And now let's move on to more about the application layer. So we're still in the overview. You see that in designing an application, we need to define the application protocol for that application. And there are 4 basic elements in designing such an application protocol. You need to first design whether you want to operate in a client-server way or peer-to-peer way. Now you heard a little bit about these different kinds of applications, and the way they work are different. So let's take a look at these different models, okay, and how communication can be working, okay, over 2 different kinds of models.
All right, let's come back to the lecture. 2.1, Principles of Network Applications. Let's first talk about the architecture. There are 3 options. We'll talk about content distribution network later in the chapter. So first is client-server, second, peer-to-peer. And there's actually a third one. Some applications actually implement using this client-server P2P hybrid architecture. You'll see an example in a little bit. So, client-server architecture. So, what you're seeing here is these are server, these are clients. All right. So the characteristic of the servers are these. These are end systems that are always on. If you think back, when you're working at PA1, no matter whether it's the day, it's the night, or it's the midnight, hey, that workstation 140.112.42.161 is always running. Okay. And it's on a permanent IP address. I just recited the IP address. I don't want to do it again. Always on. Permanent IP, that is the major characteristic of these servers. Servicing end systems. And sometimes when the service is really, really large, okay, so for PAs, you just need 1 server. For example, if you are using a Gmail account, emailing me, yeah, Gmail servers, it actually takes a whole data center. Inside the data center, there are often hundreds of these server machines, hundreds of these workstations. It might take a huge data center in order to scale, to make sure that it can serve billions of users and sending emails simultaneously. All right, so that was server. Usually very big machines, expensive machines. Clients, on the other hand, yeah, of course they communicate with the server, but unlike servers always on, clients are often more intermittently connected. So car here, having a pad, as you travel through, 4G connectivity might be weak or strong and weak again, and disconnected and strong again. Yeah, that is very unstable, intermittently connected client. And very likely, you guys are connecting to the internet using your smartphone through various IP addresses. It actually depends on where you go. On campus, if you are connecting to NTU PEEP, then NTU PEEP give you one IP address. That's going to be starting from 140.112 because you are on campus of NTU. As you walk out to have lunch, then it might be running on 4G. Then it really depends on who's your phone service provider. Then it could be operating on something like 72 dot something dot something. All right. So as you go the whole day, you might be using a handful of these IP addresses. And clients do not communicate directly to each other. Rather, they connect to the servers. Now, those clients who connect to each other are then working in this alternative architecture, the peer-to-peer architecture. So you see the elements involved here in a P2P application are simply weak end systems. We're not seeing these big machines involving in a P2P application. Yep, sorry. In P2P architecture, well, maybe I don't need to say sorry that much. Yeah, back to the lecture. In P2P applications, there are no longer anyone being always on. All right, all of us are clients, but we are clients trying to help each other. Okay? People helping people. So we have arbitrary end systems directly communicating to each other. So the peers are helping each other, requesting help from each other, request services from other peers, and other peers provide services in return. And the fact is that this peer asking for the service might also be requested by other peer here for services. So again, people helping people. So these guys helping each other. These guys helping each other. And again, helping each other. What's really nice about communicating this way or providing services this way is this: self-scalability. You see, because if I join a P2P network, let's assume Poly is this laptop. Okay, I can request services from this desktop. Okay, so let me see. I want this web page, for example, and let's assume that the web is P2P. What's going to happen is, hey, this guy here or this guy here can also be requesting the web pages that I have already downloaded because I have a copy of it, right? So why don't I provide the web page to other guys? So that's called the P2P. I give you a hand, and you being helped by me manage to finish PA1, then you can go on and help other teams for the PA1. So I'm not saying that you want to copy each other's assignments, but just what I'm saying. So you guys teaching each other or helping each other to find out what is the username and password for the team account. Yeah, that's P2P helping. There's a self-scalability in terms of whenever I join the network and asking for services, I'm also providing my capacity to help others for the service. So new peer brings new service capacity as well as new service demands. So yeah, I'll be requesting services, I'll be asking for resources, but I'm also paying back with my resources. So many people like P2P, especially young people like P2P because it's kind of fair. Okay. So, I mean, if I have resource, right, why not just help each other? All right, so peers in a P2P network, unfortunately, needs to be intermittently connected. It's going to be very hard. You guys sticking to the same IP address. So the IP address is going to be changing. So one of the big headache designing a P2P application is this: management of the peers, right? So if this is poly, and I'm running suddenly from IP address number 1 to number 2, there needs to be some sort of directory such that it maintains what's my current IP address. So my friend here will be able to contact me smoothly. Okay. Ended up, we have a complex architecture using P2P in the end. You'll see later the BitTorrent example, how complex it can be. Now the third kind, the hybrid client-server and P2P. Oh, okay, this is actually a very good example to talk about how P2P can be complicated, and some application chooses a hybrid architecture such that the complicated part, the directory lookup part, the IP address lookup part, okay, is client-server based. So in Skype, okay, so Skype is actually hybrid P2P and client-server. It actually maintains centralized servers, and in fact multiple of them, so that when we are logged into Skype, we see this directory of our friends that we might need to make a call to. Yeah. Well, once we click on the friend's head, what it does is the central server here would look up what is the current IP address of your friend, and then inform your program. Yeah, the program sitting on your laptop or sitting on your mobile phone. What is the IP address that you need to call to directly? Okay, so you're calling your friend's IP address directly. So the calling part is P2P, but the lookup part, the part that you need to look up the IP address of your friend, that part is client server. Interesting, isn't it? All right, so that's the architecture of applications. Let's talk about process communication. So we do have sometimes, especially applications running in the client-server model. We have the client process, we have the server process, and these processes we need to communicate. P2P applications, peer-peer processes, they could be the same program, but they also need to communicate. So processes running on a host in the internet will then have to communicate with other processes also on the internet. Now, if the two processes are running on the same computer, there are other ways of doing the communication. If you know operating system well, you know that there are sometimes calls you can make, just like command line function calls we often use, such as cd, mkdir, creating directories. So there are command line functions you could call that allow you to do this inter-process communication. You don't necessarily send messages. Instead, you call a function and provide certain parameters. Okay. Now, on the internet, however, for processes that are sitting on different hosts, then we do need to exchange messages. Okay. So, client and server, each will have its own process. The client process oftentimes is the one initiating communication, because server is always just sitting there, right? Server does not say, hey guys, would you like to see this web page or not? No. Yeah. Clients issue requests for a page. Server sitting there waits for a connection request, waits to be connected, waits to be contacted. So one is passive, the other needs to be active. So in client-server model, this is very obvious. In peer-to-peer model, however, one is actually actively probing another peer. Well, they are sitting there, but hey, it's barely satisfying the definition of a server. So we don't call a peer process a server process. And because a peer also provides services, so we don't call the peer process a client process. So therefore, we call these P2P applications processes the peer process, right? So applications with the P2P architecture will have peer processes In these peer processes, we'll be implementing both the client and the server functions.
So that's all the videos we have today, but don't go yet. There are more questions popping up because you guys are very curious about whether Poly play games but more important, P2P. Yeah, because it's a model that's less used and therefore you had less experience about. So I think first is, we can probably skip the game discussion. And the first question is from Qi-en, right? Is torrent one of the P2P's applications? Yes, BitTorrent is the classic P2P application. If you notice that when you use BitTorrent, you are also uploading some of the files, and those are actually requested by other people on the same torrent. So in a way, you and these other people, other users on the same torrent are sharing files to each other. There's no one server there serving files to every user, and you guys are sharing files among each other. So your hard disk is used also by other people. Chen Tao is asking, if A shares some stuff with B, then is there a chance that B gets some, from A's computer? It's possible. It's possible. It really depends on, the designer of the app. If they find that it's better that everyone openly share hard disk and let the app decide, there might be some algorithms deciding that if you have this much disk space you're ready to share, and another guy having another disk space to share, there could be some sort of centralized mechanism to allocate which file goes where. So you might getting files that you don't really want, you did not request for in those applications. I think in Bitcoin, okay, not BitTorrent, Bitcoin's case, if you host a Bitcoin machine, if you mine Bitcoins, you are essentially contributing to the Bitcoin P2P network. Yeah, and you receive broadcasts from the other Bitcoin nodes, and you are keeping stuff from these other nodes in the meantime. Yeah. Whether you want those or don't want those, sometimes you don't have a saying. Once you decide to join, then you obey the rules. So P2P is a way to start an underground society as well. If you read the news, some that are a little bit more critical will say that, hey, Bitcoin or any of these cryptocurrencies, they are actually allowing money laundering in a public way. It's very interesting discussion when it comes to P2P. It's very powerful. You could start, you can do a lot of things on them. And there's no requirement of a central control. So if the government wants to break down, like for example, a cryptocurrency, there's no target to go at, because everyone is guilty, and there are so many out there, and they try to make sure these records are anonymized. It's not that easy, but nowadays governments are getting stricter, so all these crypto coin traders are all required to record the transactions and record who owns a trading account and the timing and all these. So it will be easier now for the government to track you down, but we'll see. Maybe there'll be other cryptocurrencies showing up and come up with a different way of doing trading. So let me see. Yu Xiang asked, sorry, I went a little bit too fast. Yeah, Yu Xiang was saying, not quite understanding P2P. Are there examples using only P2P? Yeah, so it's essentially one machine directly connect to another machine by calling to the IP address. Okay, of the machine. So when we are browsing the web, we know the IP address of the web server. So the browser here issue requests for a web page directly to the server. And the reason that we know the IP address of the web browser is because we know the name of the web browser. And there's this DNS service that I mentioned earlier, which we'll cover in chapter 2, that translate from name to IP address. Okay, so these are all done a priori. But you can see that in P2P it's harder. If I want to call to make a call, internet call to a friend directly, I need to know. You need to know your friend's IP address. How do you communicate that? Okay, so usually these P2P services will have a directory part. So it's a directory that there might be still a server that you kind of connect to first to fetch the initial set of, for example, list of your friends and that you can call to. Okay, list of your friends also on the service end, so you can call to. Or list of your friends on the same torrent that you can download file from. Okay, so those directories can be in very different forms. But once you get that, that means you get IP addresses of the target, the other peer, and you call directly there. Okay, your peer or you do not get calls all the time from everyone who wants the service. It's just between a peer to another peer. We'll definitely talk more because there's a section in chapter 2 that covers P2P. All right, Yuxiang. So BitTorrent, Napster, Bitcoin, all these are P2P applications. Yeah, so Yanjun was a little bit confused about process versus application. So usually when we say application, we mean the program, okay? And when you start an application, there's a process running on the computer. Okay, so that's the only difference in fact. Because that program, you can start multiple instances. So there could be multiple processes running at the same time. For example, those who use Chrome, right? Every new subpage, I don't know what this is called. So another another page or another, 分页. This is something that I don't know exactly how you say in English. For each, it's a process. Okay, so one application install on your computer, you can click it multiple times and it will start multiple instances, multiple processes. Okay. All right, so that's all we have today. And next week we'll continue getting into application layer. The rest of the overview, because today we only talk about the most important component. You need to decide what architecture, what communication model you want to use for your application. Okay. Now that has something to do with the nature of the app you are designing. All right, so you might want different model for different apps. Okay, as you heard, right? Bitcoin definitely wants something different. Otherwise, it's easy to be taken down. So it depends on the app you're designing. You first think about what is the better communication model, aka the architecture. Okay, essentially client-server versus P2P. There are 3 other design elements. We'll cover those next week. All right, so go get lunch, and I'm gonna leave the video on for just a little bit longer so I can capture you guys' questions and comments on chat. So go. Yeah, everyone have a nice weekend. now I've got it, so let me just end the stream.